Welcome, engineering students, and welcome to this explainer. Today, we are literally opening up the hood of computational mathematics. We're looking at the Newton-Raphson method. If you've ever wondered how your simulation software or structural analysis programs spit out answers to practically impossible equations, well, this is the engine running in the background. Our goal today is to bridge the gap between abstract calculus and real-world engineering problem solving. We're going to look at how this incredibly powerful tool works, we'll take it for a test drive, and then we'll flip through the troubleshooting manual for when it inevitably breaks down.
It really all starts with this fundamental question: how do computers actually solve complex equations when standard algebra just hits a brick wall? As future engineers, you're going to encounter fluid dynamics, thermodynamics, and structural limits where isolating X is just mathematically impossible. When you can't solve it directly, you have to rely on numerical methods to hunt down the answer. Okay, let's dive into this. Here is our roadmap. First, visualizing the tangent line. Second, the Newton-Raphson algorithm. Third, the floating ball example. Fourth, divergence and zero slopes. And finally, oscillations and root jumping. Let's get right to it. Section 1, visualizing the tangent line. To truly master this method, we have to start by stepping away from the raw numbers. We need to reframe the math from pure algebra into a dynamic, geometric story. So here is the core Newton-Raphson formula. At first glance, I know, it's just an equation. You take your current guess, x sub I, and subtract the function's value divided by its derivative. But what's really fascinating here is that this isn't just a static formula. It's more like a dynamic, iterative homing missile. It takes where you currently are, looks at the slope of the curve at that exact point, and uses that to project a brand new, much more accurate estimate of where the true root actually lies. The source material describes this beautifully. It says, a tangent to the function is extrapolated down to the x-axis to provide an estimate of the root. Just imagine you're standing right on the curve of your function. You look at the slope right beneath your feet, and you lay down a straight physical slide matching that exact angle. You slide all the way straight down until you hit the flat ground, the x-axis, and where your feet touch the ground, that is your brand new, much better guess.
Moving on to Section 2, the Newton-Raphson algorithm. Now that we have that geometric intuition of sliding down the tangent line, let's actually open up the computational engine to see how it works step by step. There are basically 4 strict steps a computer executes here. Step 1, evaluate the derivative symbolically. Step 2, take your initial guess and plug it into our homing missile formula to find the new, better root. Step 3 is absolutely crucial. Calculate the absolute relative approximate error. Basically, it's asking, how much did my guess change from the last one? And finally, step 4, compare that error to a pre-specified tolerance. If the error is still too high, the computer just loops right back to step 2. It loops and loops, sliding down new tangent lines until the error vanishes entirely. Section 3, example, the floating ball. Now, algorithms are just abstract concepts until we give them something heavy to lift, right? So it's time to take this out for a test drive with a practical engineering scenario. Imagine you're working for the creatively named Down the Toilet Company. You manufacture floats for commodes. You've got a floating ball with a specific gravity of 0.6 and a radius of 5.5 centimeters. Your engineering task is to find the exact depth x to which the ball is submerged in the water. The physics gives us the polynomial equation you see right here. F of x equals x cubed minus 0.165x squared plus 0.003993. But wait, before we fire up the algorithm, we need an initial guess. And as engineers, we can't just guess blindly. The physical limits of our ball are 0 depth or fully submerged at its diameter of 0.11 meters. Now, those extremes are pretty bad choices because they sit right at the boundaries of reality for this specific physical system. We need a thoughtful starting point that's right in the middle of our physical constraints. So let's use 0.05 meters as our logical initial guess. It's roughly half the diameter of the ball. It makes total physical sense. Let's move to the next step and see how this builds as we plug it into the algorithm. The results of this calculation perfectly demonstrate exactly why the Newton-Raphson method is an industry standard. In iteration 1, our guess updates to 0.06242, giving us an error of nearly 20%. But look at iteration 2. The error completely plummets to 0.07%. By iteration 3, our error is statistically 0. The absolutely crucial takeaway here is this behavior. The number of significant figures of accuracy roughly doubles with each iteration.
This rapid lock-on is known as quadratic convergence. It's just brilliantly fast. Section 4, divergence and zero slopes. However, as we all know, the faster a sports car is, the harder it crashes when things go wrong. We are now shifting gears into the owner's manual troubleshooting section to see what happens when our perfectly good algorithm dramatically stalls out. See, the method relies heavily on the behavior of the specific function you're analyzing. Because of this, it can fail in several distinct and sometimes quite spectacular ways. The main culprits are inflection points causing divergence, flat slopes causing division by zero, endless oscillations around local minima or maxima, and root jumping. Let's break these down one by one. First up, inflection points. If your initial guess happens to be near an inflection point, where the curve shifts from concave to convex, the tangent line can be incredibly shallow. As we see in the source data, a guess near 1 for a particular function can fling the next estimate way out to -30. The solution diverges rapidly, and then it just slowly, painfully plods along for dozens of iterations just to find its way back to the actual root.
And that perfectly sets up our next failure state. As the text states, a zero slope is a, quote, real disaster. Remember our geometric visualization from earlier? If you're standing at a local minimum or maximum, the ground beneath your feet is perfectly flat. Your tangent line is just parallel to the x-axis. It shoots off horizontally to infinity and literally never hits the ground. Mathematically, the derivative is 0, meaning you are forcing the computer to divide by 0, instantly breaking the whole algorithm.
Section 5, oscillations and root jumping. Flat slopes and inflection points push our estimate away. But what happens when the method simply gets endlessly confused? Let's move to our final 2 types of failures. Take a look at this table tracking the equation x squared plus 2. Because this parabola sits entirely above the x-axis, it obviously has no real roots. If you blindly ask Newton-Raphson to find one, it just oscillates wildly. The tangent line shoots the guess to the left, then a new tangent shoots it to the right, just bouncing back and forth across the local minimum. The error wildly jumps into the hundreds of percent, reaching 829% by iteration 6. The computer will just spin its wheels infinitely here. Finally, we have root jumping. If you're dealing with a highly oscillating wave like the sine function, there are multiple roots crossing the x-axis. If your initial guess is off by just a little bit, the steep tangent line might skip right over the root you want to find and accidentally shoot you far down the curve, converging on a completely different, unintended route. You ask the computer for the answer near 2 pi, and it confidently hands you a mathematically correct but practically useless answer of 0. So, what is the ultimate remedy for all these spectacular failures? Well, the answer actually isn't better code, it's better engineering. There is no magical general convergence criterion for Newton-Raphson. The only way to avoid the traps of zero slopes, divergence, and root jumping is to use your engineering intuition, or maybe just a quick graphical plot, to provide a rock-solid, sufficiently close starting guess.
And that leaves us with a critical thought to end our explainer on. We've seen the brilliant quadratic speed of this algorithm, but we've also seen how easily a flat slope or an inflection point can just completely derail it. So, if numerical tools are so incredibly fast, yet this fragile, what happens when we blindly trust an algorithm without actually understanding the physical reality it represents? It's a great reminder that the computer is just the engine. The engineer still has to steer. Thank you so much for joining me, and keep exploring the math beneath the surface.